general group, you do have you have the 1-6, but here only for SU2 because this special traceless condition. That's why you don't have it. And so, but this is basically the idea that you can using the gauge topological term to understand SPD phase, rather than using this nonlinear sigma model topological term. And but certainly once you have a gauge topological term, you can have this so-called spin quantum Hall state effect, because this gauging is like a probing. It's like adding spin electric field, and you measure spin current. So I won't go through this. Actually, the appearance of this gauge topological term basically say that you have a spin Hall, a quantized spin Hall conductance. And then it's also, the appearance of this gauge topological term also imply that there's a gapless states at the boundary. And the reason is also very simple once you have this. Because this gauge topological term is gauge invariant on the closed space-time. When the space-time has a boundary, then this Chen center is not even gauge invariant. And so that's a problem, because the response theory should be gauge invariant. And so that means that on the boundary we should have some non-trivial theory, and that theory are anomalous. And so the theory on the boundary is not gauge invariant. And this non-gauge invariant of a boundary theory cancel the non-gauge invariant of the Chen-Simon term. And then whole thing is still gauge invariant. So this is a well-known anomaly inflow. And so therefore, using this picture, we can see that this theory actually have a non-trivial gapless boundary excitation, and which is also have an anomaly. So basically, this is a picture here. And that in the bulk, we have a pure topological term, and that is the bulk theory. However, when you have a boundary, then the effective action for the edge actually is without this term. It's just this the bulk topological term became a West-Union term for the boundary for the boundary theory. And when you only have a pure topological term in the bulk, naively the boundary theory only have this pure West-Union term. Okay, and this is exactly what Chen talked about. That when you have a boundaries, then this bulk topological term become the boundary West-Union term. But however, although this pure bulk topological term is a fixed point theory for the bulk, but however, the pure West-Union term on the boundary is not fixed point theory. And there's amazing things that the fixed point theory for the boundary is this one. So this kind of dynamic term is spontaneously generated for some reason. Okay, and so actually this is the belief. So once you have this West-Union term, then the fixed point theory on the edge is this one. And this particular theory have a very nice property pointed out by Witten, is that if you it has so-called right moving current and the left moving current, where Z is the x plus IT. Okay, so just these two combination of a G inverse and a G inverse G, and it turns out that when this coefficient and this coefficient have this matching, you can show that the equation motion of this nonlinear sigma model have this form. This particular current is purely Z, so Z bar, partial Z bar equal to 0. And that particular current is a pure Z bar and partial Z equal to 0. So that represents this kind of combination only depend on Z, so that's only right mover. And this particular combination only depends on Z bar, so that's only left mover. So this left mover, right mover totally decoupled. And so this is the emergent SU2 cross SU2 symmetry at a fixed point. And it turns out that if you look at this particular form, you can see that because in our case SU2 symmetry is this left, sorry, no comma, is a left modification of H. So therefore, this one, let me see. Okay, this one actually, this current transform non-trivially under this kind of transformation, at the joint transformation. So this current transform at the joint representation of this left modification. So this really SU2 charge and a current. But this combination, you can see under this transformation, this H just cancel at the inside. So this don't change. So this one actually is neutral under this particular SU2. So therefore, we see that the right moving current carry SU2 charge, but the left moving current do not carry SU2 charge. So that's kind of chiral. Left and right are not symmetric. And so this is anomalous. The only right mover carry SU2 charge, left mover do not carry SU2 charge. So as SU2 symmetry is anomalous. And so this is why we see that the H state, we have an anomalous SU2 symmetry. And so this is really a character of an SPD phase. The SPD phase have non-trivial bulk property, but the H theory are always anomalous. So, and then all the special property of H is because the H theory is anomalous. So whatever anomalous property can give you to the H, then you will have that as a character of an SPD phase. So this is a key observation that the different bulk topological term will lead to the different edge theory with different anomaly. So the edge anomaly and the bulk SPD have one-to-one correspondence. And so using this example, we can see this.
Is the SU2 cross SU2 symmetry still there when you gauge the theory?
The SU2 cross SU2 because there is another SU2 is like a right multiplication, which we call SU2 or L whatever. And this SU2 is not SU2 we are talking about. So basically the second SU2 may not even there, because we can add a term in this Lagrangian which break the SU2 of a right multiplication. So therefore, actually, in the bulk effective in the bulk action, we don't have the second SU2. But however, on the edge, low energy edge effective theory have an emergent SU2. So this SU2 exists in the low energy sector of a boundary state, but this second SU2 is the emergent SU2. So the true SU2 required in our model is only the first SU2.
Right, but the immersion, my question is whether the immersion SU2 will still be there after you have gauged the field.
We never gauge anything. When you say gauge, it really means we don't really mean gauge in 100 sense. Because gauge field don't fluctuate. When we gauge, we just add some background twist. So this gauge field is not dynamical, so it's not really a gauge theory. And okay, then using this understanding for SPD anomaly, then we can address the issue about so-called beyond group cohomology SPT. And so the picture is following. So we have these SPD states described by this group cocycle. And then using this SU example, we see that the H theory actually have a gauge anomaly or symmetry anomaly. So this symmetry of the SPD phase, after gauge it become gauge field, and this gauge theory have an anomaly at the boundary. Okay, so that's the correspondence. And similarly, actually, we have a similar story for the topological state. For the topological states, it also has edge theory. But there, the edge theory have a gravitational anomaly. Okay. So this correspondence is very important. So topological order corresponds to gravitational anomaly in the one lower dimension. And SPD order corresponds to gauge anomaly in one lower dimension. And these two are one-to-one correspondence. So actually, understanding SPD phase and understanding topological order basically is classify all possible anomaly in one lower dimension. And with this understanding, we can also easily understand what is missing. That is, it's a mixed gauge gravity anomaly. Because in general, we could have a time anomaly which is both gauge and gravity kind of mixed together. And so far we have not talked about the mixed gauge gravity anomaly. So there should be some kind of a topological phase where the boundary have a mixed gauge gravity anomaly. And this phase actually should be SPD phase. Because if you destroy destroy the symmetry, then we don't have gauge part. But then if you have a mixed gauge gravity anomaly, if you remove the gauge part, the anomaly term also gone. So the mixed gauge gravity anomaly require gauge part, so require symmetry. Yeah. So it require the symmetry. So therefore, this mixed anomaly can give us this. So this mixed gauge anomaly, gravity anomaly, should correspond to SPD phase. Okay. But how to understand this this SPD phase with a mixed gauge anomaly? So here we just say that the SPD phase described by group cocycle we call the pure SPD phase because they have a pure gauge anomaly, and the pure gauge anomaly have a topological term which is just like Chen-Simons term, which is a pure gauge term. So this is pure gauge topological term, and that gives us a pure SPD phase. And then the invertible topological order, the boundary have a gravitation anomaly, and we talk about that. So the topological term, the bulk topological term, which contain the gravitational Chen-Simons term instead of IC2 Chen-Simons term, or some kind of Stiefel-Witten class term. So this is a pure gravity term which depends on the connection of a space-time connection. Then that's give us a topological order, corresponding to topological order. That's a gravitational anomaly. So the boundary of the Chen-Simons theory will have a gravitational anomaly. And so the boundary, so this gauge topological term only depends on the gauge connection. So the boundary of a Chen-Simons term would give us a pure gauge gravity anomaly. And by listing these two, it's easy to see that to get a mixed one, we just mixing these two together. For example, we can mix this gauge Chen-Simons term with a Pontryagin class. So this is a 7-dimensional. So there's some 6 plus 1 dimensional SPD phase, which are described by this. So that's SU2 SPD phase involving the Pontryagin class and the gauge Chen-Simons term. So this kind of a topological term depend on both on SU2 connection and the space-time connection. So this should correspond to some kind of mixed SPD states. And that's it. So we just, instead of looking for all the pure gauge term or pure gravity term, we're just looking for all this mixed term. Then we get understanding and the classification of this mixed SPD phase. And this mixed SPD phase is this gravitational, is this beyond group cohomology term. And so how to obtain a theory which produce, so here we are looking for some kind of a field theory which couple to the symmetry twist like A, and also couple to space-time curvature like gamma. And such that after integrate out the matter field, we should obtain this kind of effective theory. So how to obtain such a theory? And well, there's a way to do that. And so remember that if you start with nonlinear sigma model where G belongs to group, then we can add this nonlinear sigma model topological term, and after gauging this symmetry, after integrate the matter field G, we get this gauge topological term. And so that this is the story we have. Okay. But to obtain the mixed gravity gauge gravity term, so what we do is following. We start with a nonlinear sigma model, which is a group, the target space is G times SO. G is still symmetry. SO is because the tangent bundle of the space-time is the SON vector bundle. So the connection in the space-time connection actually is the SON connection. It's some kind of SO connection. So therefore we just thinking this curvature in space-time actually is like SO symmetry twist. So therefore we just add this SO part. Okay. And then when we adding twist, say that we still have this A symmetry twist which coupled to the G part of a target space. But the space-time curvature or space-time connection gamma coupled to SO part of the curvature. And then we can write down all possible topological term for this G times SO. So this G times SO still described by group cohomology. This nonlinear sigma topological term basically is a topological term from G times SO. But again, they couple to A, the couple twist like A and gamma, A couple to G, gamma couple to SO. And then we integrate the matter field G. Then we get this topological term which contains both A and gamma, and that's it. So this way we obtain most general theory. And so therefore, from here we can say that the topological term of a nonlinear sigma model is classified by this kind of group cohomology, G times SO. So looks like, naively it looks like for every element of a G times SO, we should get a different gauge topological term. And it's not quite that. Actually, it's almost, not quite. And so at least we say that by choosing different group element, basically we're choosing different nonlinear sigma model topological term. Then the problem is that after integrating matter field, this gauge topological term we obtain is a little tricky. Is that sometimes the different nonlinear sigma model topological term may produce the same gauge topological term. Yeah. So this is possible because of following. When we consider nonlinear sigma model topological term and the gauge topological term, we say they are one-to-one correspondence. But this one-to-one correspondence is the same. Is assuming that when we're probing this gamma part, this SO part, we are using arbitrary SO twist, means arbitrary SO vector bundle on the space-time to probe this SO part. But however, in the space-time, we are not talking about the arbitrary SO bundle. We only talk about the tangent bundle of space-time. The tangent bundle of space-time is not arbitrary SO bundle of space-time. It's only some special subset of SO bundle of space-time. So therefore, this subset of SO bundle on space-time can only distinguish certain topological term, and some other topologies are not distinguishable by only tangent bundle. So therefore, so there's a reduction, there's some equivalent. So therefore, we should quotient out something. So basically, the classification is this one, but quotient out something. And what you quotient out is basically is a topological term which are not detectable by the tangent bundle. It's detectable by arbitrary vector bundle, but not detectable by tangent bundle. So there's something known in mathematics. So mathematicians study these kind of things. But this again is some topic in algebraic topology. Because of time, so let's just finish here. Is that if we do that, we'll get this table. And so this black one is the group cohomology, is a pure SPD phase. So that's a black entry. And the blue entry and the red entry is the actual one. And what I want to emphasize that all these entries are really subset of this group cohomology. So basically, the table is really a subset of this group cohomology. It's really this group cohomology quotient out something. Okay, but what to quotient out? There's some actual mathematics to go through, but it's something is doable. And so after you do this quotient, and so that's how we get this table. And in particular, I want to say that for the U1 semi-product Z2T, this is symmetry for bosonic topological insulator. So we see that the pure SPD phase gives us Z2 square, and then this actual Z2 is this beyond group cohomology state discovered by Ashvin and Sansio. And so actually in 3 plus 1 dimension, we only have this actual Z2 when we have a time reversal symmetry. I don't know whether it's zero or not, but so far I worked through some groups. I couldn't find actual states for unitary theory. But however, in higher dimension, we do have actual theory, even only for unitary theory. For example, like Zn. Even Zn in 4 plus 1, we have actual one. And so this blue one are all actual SPD phase, are so-called mixed SPD phase beyond this pure SPD phase. Yeah. And so this probably is give us some kind of a systematic understanding of different SPD effects. Okay, I will stop here.
Any questions?
Yeah, yes.
So if I understand correctly what you're doing, so now later you put on this loop operator on the curve manifold with SO and isometry, is that right?
No, I didn't put in loop operator. What I did is that I gauge the symmetry. So what I really did is gauge symmetry really means that when you do path integral, the matter field should have a periodic boundary condition.
Yes.
And so gauging really means that I impose some kind of a twist boundary condition for the matter field.
Okay.
So this A I have is really describing the twist boundary condition. So the standard Pascal calculations are you always assume around the non-contractile loop the field is periodic, but here I just cut through. I just have some kind of submanifold, and we say across this submanifold the boundary condition twisted.
Okay.
So then we ask when you have a twisted path integral, what do you have? And then in this case the partition function no longer equal to 1. And it became something non-trivial. And so basically, I'd rather say symmetry twist. So I'm using symmetry twist as a probe, and the partition function as a response, and using this to construct topological environments.
So this is a bit different when people put in a Wilson loop in the.
There's no, yeah, it's different from Wilson loop.
Because otherwise, whatever this kind of extended object, then has to be invariant.
Yeah, it's not a knot theory. It may be related, but we are not putting Wilson loops, and we do twist boundary condition.
Because some of the steps here are quite similar when people are doing localization on curve manifold.
That's true. That's a dual. So what we do here is dual for Wilson loop. Because Wilson loop corresponds to study the statistics of quasi-particles, and here we do not create quasi-particle. We're just changing space-time topology.
But you didn't sum over the twisted boundary conditions. So it didn't
We don't sum.
do the gauge.
We do not sum. So this is not gauge theory.
Yeah.
So if we sum over twist boundary conditions like integrate over this A, we do not do that. So naturally this is not gauge theory. It's we do not sum over twist boundary condition.
Question?
Yeah, so what if we consider the G and SO, they are not direct product? Does that make any sense to think about that? Or?
Yes. And that would correspond to the mixing the point group symmetry and the internal symmetry.
Yeah, I see.
So therefore you have a basically if you don't have point group symmetry, you only have internal symmetry or point group symmetry, then maybe there's some you would allow some kind of a non-trivial twist of SO part. But however, you can think of you have a point group symmetry and internal symmetry, or maybe not both. You only some mixed point group symmetry and internal symmetry are your symmetry. So mixed of point group and internal symmetry is a symmetry. And then yeah, something like time reversal with some other rotation. So then that corresponds to this more general. It's not semi-direct. So basically, the group we have should be have this extension of some kind of group extension and some twist product or more general group extension. Yeah. So basically, it's the SO extension of a symmetry group. That's maybe more general targeted space. That is certainly possible and also physical, and so there's a more general situation.
Yeah, because when we discuss SET, actually we extend the symmetry group by the gauge group, but not in the direct product.
Yeah, that's right. And see here is similar. Yeah. Okay.
Here for space-time dimension D, so the actual structure group is like SOD. So here you consider SO infinity.
Exactly.
You have to really think about classifying space. So
that's right. The reason is the following, and this is very important, is that there is a so-called stabilization condition. Is that it's a more natural for the dimension, say d plus 1, it's a very natural thing about the SO d plus 1, but however, you can always embed SO d plus 1 into SO bigger, SO n is bigger than d plus 1. And then here what we say is that we can always adding these actual dimensions, but those actual things are not twisted. They just adding there. Just some you have some actual degree freedom. They are not twisted, so it's allowed. And so when we deforming two different SPT phase into each other, we allow to deforming via this higher the theory with a more degree freedom. Certainly you can do deformation within non-necessary model of SO d plus 1. But we should also allow the deformation within the non-necessary model with SO n. N is even bigger, or n can be infinity. So this through this consideration, we feel that consider SO in infinity is better. And we can always when you do this, so when you do this space-time twist, this SON twist can always be embedded into SO infinity twist. So this should be okay. So it is this kind of stabilizing consideration motivate that to consider only SO infinity.
Can I think about this? Actually, it's kind of like a structural group in the classifying space, because the classifying space DG is infinite dimension.
I don't know. I think SO and also have its own classifying space. They are different. And but here I'm talking about the SO infinity classifying space. So going to classifying space do not correspond to making n go to infinity. N go to infinity is really it's some physical consideration, and it's kind of like a stabilizing consideration.
Kind of this base manifold, you can always have some additional hidden kind of dimension.
No. I just say that because this SO part is not base manifold. It's just some degree freedom. I can always adding actual degree freedom, and then we say this actual degree freedom do not couple to the base manifold initially. But when you do deformation, we allow this actual degree freedom to couple to base manifold, and this kind of deformation should be allowed. Yeah.
But can you consider like other structure, maybe even larger than?
Yeah, you can consider other one. Yeah, not SON, but some SON. But as long as you can embed SON into this, should be fine. But then there should be issues, and I don't know if you think about the other group how. You really have to trace back to physics. This I don't know.
Because the most general structural group is like a GL and not S.
Yeah, that's right. The issue is the following. Yeah, that's a very good question. Is that because here because the vector bundle is always SON. So if you use a GLN, you have to always study all the GLN class characteristic class and try to say which of those can be distinguished by the SON vector bundle. And so that's a good idea. So maybe one can understand this result from this more general setting. Yeah.
How does one implement the symmetry twisting experimentally to test this template?
One cannot. So this universal probe is not experimental probe, it's a numerical probe. You can implement that in the numerical calculation. And so this is different from X-ray. X-ray is universal probe and they are experimental probe. So therefore people can do experiments. But however, the universal probe we propose here for SPT states are numerical probe, not experimental probe. And so the experimental probe basically, at the moment is better study the edge states. But the edge state is a little bit tricky because the property of edge state is very complicated. They are not one-to-one correspondence or correspond to the SPT order. So you have to extract, by measuring edge state, you have to extract the anomaly. And so